Hello, and welcome to this presentation, The Rebirth of HF. This presentation is intended to give you a brief technical introduction to HF, or high-frequency communications, HF propagation, and the new and exciting advancements that have led to a rebirth of HF as a global communications technology. This presentation is divided into two main sections. The first half of this presentation is an introduction to HF propagation and its different modes. We'll spend most of this time on ionospheric, or so-called skywave propagation. Skywave propagation is what enables HF to be used for worldwide communications, but is also the greatest challenge in using HF, both traditionally and in more modern applications. Part of this discussion will involve various observations and measurements that allow better predictions of ionospheric conditions and their effect on HF propagation. After this introduction to, or review of, HF propagation, the second half of this presentation discusses HF communications. We'll start by briefly discussing traditional HF communications, followed by an explanation of why HF's role as a global communications technology declined over the last few decades. But as you may have guessed from the title of this presentation, there's been a resurgence of interest in HF, and we'll spend most of the second half discussing the reasons for this renewed interest in, as well as the technological advancements driving, this rebirth of HF. HF stands for high frequency, and is usually used to refer to frequencies in the range of 3 MHz to 30 MHz, although in many cases the practical definition of HF can be extended down to as low as 1.5 MHz. This corresponds to wavelengths in the range of about 100 meters to about 10 meters. You'll sometimes also hear HF referred to, albeit somewhat imprecisely, as shortwave. The primary use of HF is for long-range or even global communications. Broadcasters can reach listeners worldwide using HF, and this global reach is also useful for many government and military applications. Amateur radio operators around the world also frequently use and experiment with HF. As we'll see in this presentation, it's the unique properties of HF propagation that enable long-range or global communications. Although HF propagation can provide worldwide communications, HF propagation can also be highly variable, especially compared to communications at other frequencies, such as VHF or higher. As a practical matter, this means that the greatest challenge in HF is finding the optimum frequency for communication with the intended destination and under the current propagation conditions. Before we go into more detail about how this is done, let's briefly cover the three main HF propagation modes: line of sight, ground wave, and skywave. Line of sight is fairly easy to understand. Signals propagate in a straight, unobstructed path between the transmitter and the receiver. Line of sight is the only HF propagation mode which is fairly constant. Your ability to use line of sight to communicate with a given station doesn't change much over periods of minutes, hours, days, months, years, etc. That said, HF isn't a very good choice for line of sight communications, and it's rarely used for this purpose. Because of the lower frequencies, HF requires larger antennas, and bandwidth is also somewhat limited. There also tends to be much more noise at HF compared to higher frequencies. This can be a problem because the limited bandwidth at HF usually means communications are carried out over AM or single sideband, which are more sensitive to noise than wider bandwidth FM. For these reasons, most line-of-sight communications are carried out at VHF or higher, rather than at HF. If we don't have a direct line of sight to another station, ground wave is another possible solution. Ground wave, sometimes also called surface wave, involves signals propagating along the surface of the Earth. Interaction between the lower part of the transmitted wavefront and the Earth's surface causes the wave to tilt forward, allowing the signal to follow the curvature of the Earth, sometimes well beyond line of sight. Ground wave propagation is, however, highly dependent on two different factors: the conductivity of the surface and the frequency of the transmitted signal. In general, higher surface conductivity gives better results in the form of greater distances that can be covered. Salt water has excellent conductivity, especially compared to dry or rocky land, so ground wave is a good choice for ship-to-ship or ship-to-shore communications. With regards to frequency, ground wave works best for lower frequencies. For example, the theoretical range of a 150-watt transmitter at 7 MHz is 35 kilometers over land and close to 250 kilometers over the sea. At 30 MHz, however, our range falls to only 13 kilometers over land and just over 100 kilometers at sea. One of the most important propagation modes of HF is skywave, because it's skywave propagation that enables beyond line of sight or worldwide communications. In skywave, layers of ionized particles in the upper atmosphere refract HF signals back towards the Earth, allowing communications over many thousands of kilometers. The distances that can be covered by different frequencies are almost entirely a function of the state of these layers of ionized particles, collectively referred to as the ionosphere. In this presentation, we'll explain the different layers of the ionosphere, how the ionosphere is affected by the Sun, and how we can both quantify the current state of the ionosphere and predict the future state of the ionosphere. The incident angle, or the angle at which a signal reaches the ionosphere, also plays an important role in how far a skywave signal will propagate. The radiation angle of an antenna is primarily a function of both the type of antenna and the location at which the antenna is installed. Higher placement of an antenna usually lowers the radiation and incident angles. And generally speaking, the lower the incident angle, the greater the distance covered by skywave propagation. Note, however, that so-called skip zones may be created depending on the radiation or incident angle. In these zones, HF signals can't be reached either via skywave or via ground wave propagation. In order to understand skywave propagation, we should start by explaining how ionization occurs in the Earth's atmosphere. When ultraviolet energy or radiation from the Sun strikes gas atoms or molecules in the atmosphere, this energy can cause electrons to become detached. The result is a positive ion and, more importantly, a free electron. The Earth's magnetic field keeps these free electrons roughly in place. The level of ionization and the number of free electrons increases as the amount of sunlight striking a given part of the atmosphere increases. When that part of the atmosphere rotates away from the Sun, that is, at night, this energy is removed, and the ions recombine to form electrically neutral atoms and molecules. Note that recombination is a slower process than ionization. Atmospheric ionization increases rapidly at dawn, but decreases less rapidly after dusk. As mentioned earlier, the region of the Earth's atmosphere that undergoes this ionization is collectively called the ionosphere. The level or density of ionization in the ionosphere is different at different altitudes, and areas with ionization peaks are often grouped into so-called layers or regions. The layers that are important for HF propagation are the D layer from 60 to 100 kilometers, the E layer from 100 to 125 kilometers, and the F layer, or layers, from about 200 to 275 kilometers. Note that these are only rough numbers. The thickness and altitude of ionospheric layers is never constant. The reason for defining these different layers is that each of these layers will refract and or absorb HF signals in different ways. It's important to note that the ionosphere does not reflect signals, but rather refracts signals. The different electron densities at different altitudes is what makes this refraction possible. Let's start with the lowest level of the ionosphere, the D layer. The D layer only exists during daytime hours and disappears at night. Although the D layer is ionized by solar radiation, the density of free electrons in the D layer is too low to effectively refract HF signals, and therefore the D layer cannot be used for skywave propagation. Instead, the D layer acts as an absorber of HF signals. This absorption is higher for lower frequency signals than for higher frequency signals. Absorption also increases with increasing ionization, so absorption is usually highest at midday. For these reasons, the properties of D-layer absorption mean that higher frequency HF signals work better during the daytime, whereas lower frequency signals work better at night, after this layer has disappeared. The next highest layer, the E layer, is the lowest layer of the ionosphere that can refract HF signals back towards the Earth, and is the lowest layer that supports skywave communications. Compared to the other layers, it is relatively thin, usually about 10 kilometers or so. The E layer is much less dense, that is, ionized, during the day, but unlike the D layer, it doesn't completely disappear at night. Aside from mostly short-range daytime communications and a few other special cases, E-layer propagation is not commonly found in HF. Note, however, that at VHF, the E-layer is very important and supports some rather exotic and less predictable propagation modes, such as sporadic E. And these modes make long-distance communication over thousands of kilometers possible, even at the relatively high frequencies of VHF. The F layer is the most important for skywave propagation. During the day, the F layer splits into two sublayers, F1 and F2, which merge back into a single layer again at night. Compared to the D and E layers, the height of the F layers changes considerably based on things such as time of day, season, and solar conditions. More on this shortly. The lower F1 layer primarily supports short to medium distance communications during daylight hours. The F2 layer, on the other hand, is present more or less around the clock. It has the highest altitude and the highest ionization of all the layers, and is therefore responsible for the vast majority of long-distance HF communications. The degree to which the different layers of the ionosphere refract and/or absorb radio frequency signals is largely a function of that signal's frequency. The general rule for HF skywave communications is to always use the highest possible frequency that will reach a given station or destination. This is called the maximum usable frequency, or MUF. Signals whose frequencies are higher than the MUF will not be refracted by the ionosphere and will continue out into space. Usually, the MUF increases with increasing ionization. Another important frequency threshold is something called the lowest usable frequency, or LUF. When the signal frequency is at or below the LUF, communication becomes difficult or impossible due to signal loss or attenuation. So we want to choose a frequency somewhere between the MUF and the LUF. There is one very important difference between MUF and LUF. Because the LUF is mostly determined by noise, using a higher transmit power, a better antenna, etc., can improve or lower the LUF. MUF, on the other hand, is entirely a function of the ionosphere. You can't improve or increase the MUF by using more power or a better antenna. The MUF is what it is. And as we'll see shortly, if the LUF becomes greater than the MUF, no HF communication is possible. One way to determine the MUF is purely through experimentation, but there are also methods for estimating the MUF using something called the critical frequency. The process for measuring the critical frequency is as follows. Pulses at various frequencies are transmitted vertically by equipment called ionosondes. Depending on the frequency of the pulse, these pulses are returned by different layers of the ionosphere, and we can use the return time to estimate the heights of the different layers. Once we reach a certain frequency, the pulses are not returned by the ionosphere and instead continue on into space. This is the critical frequency. Critical frequency is a function of both the current ionizational level as well as the measurement location. It's measured regularly at hundreds of locations around the world. Mathematically speaking, the maximum usable frequency is the critical frequency divided by the cosine of the angle of incidence. If we send a signal straight up at 90 degrees, MUF and critical frequency are the same. But as a practical matter, the maximum usable frequency is usually estimated at 3 to 5 times the critical frequency. Critical frequency is one way of quantifying the state of the ionosphere, but this is an active test. We transmit signals and measure the return signals. In addition to critical frequency, there are 3 common passive methods that are used to quantify the state of the ionosphere. The first of these is sunspot number, which can be used to predict the level of atmospheric ionization. The second is the solar flux index, which is an actual measurement of ionization. There are also 2 geomagnetic indices, the A index and the K index, which give an indication of the impact of solar particles on the Earth's magnetic field. Taken together, these quantities provide a good indication of the current state of the ionosphere and can be used to predict HF propagation. Let's take a look at each of these 3 quantities in a bit more detail. Sunspots are, relatively, cooler surface regions of the Sun. Relatively in this case means they have temperatures around 3000 Kelvin versus the normal 6000 Kelvin seen elsewhere. After they appear, sunspots last between a few days and a few months. Sunspots are associated with powerful magnetic fields, and these fields affect how much radiation is given off by the Sun. The greater the number of sunspots, the higher the level of solar activity and radiation. Because of this, more sunspots generally means higher atmospheric ionization, a higher MUF, and better overall HF propagation. The quantitative measure of sunspots is sunspot number, which is a daily measurement of sunspots. Note, however, that sunspot number isn't simply a count of the number of sunspots. It also takes into account additional factors like the size and grouping of sunspots. Sunspot number is recorded by a number of solar observatories around the world, and sunspot numbers range from 0 to a maximum recorded value of about 250. As mentioned a moment ago, more sunspots, or a higher sunspot number, almost always means better HF propagation. It's also worth noting that sunspot data has been collected for almost 400 years, giving us valuable information on how the number of sunspots has changed over time. And sunspot numbers do change over time. In fact, sunspot activity follows a roughly 11-year solar or sunspot cycle, as shown in this graph. Generally speaking, sunspot numbers are usually around 150 at the peak of a cycle, during which time HF propagation is very good on most frequencies, including higher frequencies. At the bottom or trough of the sunspot cycle, sunspot number is close to zero, meaning much poorer HF propagation. Given the period of the sunspot cycle, it should be clear that sunspot cycle is good for long-term predictions of HF propagation, that is, in terms of years, and over this time period it is fairly reliable. It is, however, worth noting that at several points in history, for example, in the late 1600s and the early 1800s, sunspot numbers stayed low for several decades, creating so-called minimums or minima with very little solar activity. The reasons for these minima are still very much a mystery. We can also quantify solar activity by measuring the level of solar noise, or flux, at a frequency of 2800 MHz. These measurements are reported as the solar flux index, with values given in so-called solar flux units. Measured solar flux values generally fall in the range of about 50 during a solar cycle minimum to about 300 during a solar cycle maximum. Since solar flux is a measurement, not an observation, it tends to be more consistent and reliable than sunspot number, but it also doesn't have the same 400-year history of values. However, solar flux values tend to correlate quite well with sunspot numbers. Like sunspot number, higher values of solar flux mean higher maximum usable frequencies and better HF propagation. Sunspot number and solar flux index are valuable measures of longer-term variations in solar radiation. The ionosphere is also affected by shorter duration events occurring on the Sun. The most important of these are solar flares, which are a type of eruption on the surface of the Sun. Solar flares cause a rapid rise in both X-ray and ultraviolet radiation, as well as the ejection of both low and high energy particles. Solar flares are essentially unpredictable, but do occur more commonly during peaks in the 11-year solar cycle. Solar flares have a significant effect on HF propagation because they can lead to sudden ionospheric disturbances, polar cap absorption, as well as geomagnetic and ionospheric storms. As the name implies, a sudden ionospheric disturbance is sudden. It occurs about 8.5 minutes after a flare, that is, at the same time the flare becomes visibly detectable on the Earth, and is caused by the arrival of solar radiation. This radiation causes D-layer ionization, and hence D-layer absorption, to increase rapidly, starting at the lower frequencies and moving upwards. The affected frequencies are often almost completely blacked out. Fortunately, a sudden ionospheric disturbance only impacts the sunlit hemisphere, and tends to last a relatively short time, typically about an hour or so. And in some cases, smaller solar flares can actually enhance HF propagation by increasing ionization at higher frequencies without a corresponding increase in D-layer absorption. The next effect of a solar flare is something called polar cap absorption. The high-energy particles emitted by a flare reach the Earth several hours later, and the Earth's magnetic field prevents them from entering except at the poles. Once they enter the atmosphere, these particles can increase D-layer absorption in the polar regions, and this effect can last for several days. During this time, HF signals traveling through or near the poles will be blocked by the increased attenuation, but paths that do not go near the poles may remain relatively unaffected during this event. Geomagnetic storms are caused by lower energy particles arriving at the Earth. This occurs 20 to 40 hours after a solar flare. These particles can also be generated during something called a coronal mass ejection, or CME, which can occur independently of a solar flare. In either case, these particles can cause geomagnetic storms. Geomagnetic storms produce visible aurora, but they can also interfere with GPS signals, satellites in general, terrestrial power distribution networks, etc. Geomagnetic storms don't directly interfere with HF propagation, but they can create ionospheric storms. Ionospheric storms lower the maximum usable frequency and do degrade HF propagation. And as mentioned earlier, if the MUF falls below the LUF, an ionospheric storm can create a complete HF skywave blackout. One final note. It is possible to have a geomagnetic storm without an ionospheric storm, but the converse is not true. All ionospheric storms start out as geomagnetic storms. Sunspot number and solar flux index can be used to quantify ionospheric conditions, but to quantify geomagnetic conditions, we use A and K indices. In general, lower values for A and K mean a more stable ionosphere, although, as we just mentioned, in some cases a geomagnetic storm may not lead to an ionospheric storm. A and K are measured at observatories around the planet, and these local values can be averaged to produce planetary values. One of the biggest differences between these two indices is that A is calculated daily, whereas K is measured every 3 hours. Higher values of K indicate a current or ongoing geomagnetic event, whereas A is useful in knowing how long this disturbance has been occurring. Before moving on to discuss HF communications, let's summarize what we've learned about HF propagation. Global HF communications are usually based on skywave propagation, rather than direct line of sight or ground wave propagation. In skywave, signals are refracted by the ionosphere, although the effect of some layers is more to absorb signals than to refract them. Whether or not a signal is refracted or absorbed by the ionosphere is largely a function of 3 things: the frequency of the signal, the incident angle, and the amount of ionization in the upper atmosphere. Generally speaking, this ionization increases during daylight hours while the sun is illuminating that side of the Earth. On a larger time scale, ionization also increases as the number of sunspots increases, the number of sunspots following a roughly 11-year solar cycle. Aside from these semi-regular effects, certain types of solar events can unexpectedly or unpredictably disrupt the ionosphere, and hence HF propagation. Solar flares are the most common of these, and flares can lead to so-called sudden ionospheric disturbances, polar cap absorption, and both geomagnetic and ionospheric storms. Coronal mass ejections are less common, but often a more severe source of geomagnetic storms. And finally, we can quantify the current state of the ionosphere and/or make predictions about HF propagation based on measurements such as sunspot number, solar flux index, and the A and K magnetic indices. Now that we have a basic understanding of HF propagation, we'll spend the remainder of this presentation talking about how recent technological developments are helping us to overcome some of these challenges presented by HF propagation. Although HF once dominated global communications, satellites began replacing HF in several applications in the 1960s, and this trend accelerated rapidly over the next several decades. There were 3 main reasons for this. The first is that satellites could offer much higher data rates than was ever possible over HF. Satellite communications were relatively immune from changes in propagation. This is in sharp contrast to the highly variable and somewhat unpredictable nature of ionospheric or skywave propagation at HF. And because of the more stable and straightforward nature of satellite signal propagation, satellite communications generally did not require highly trained or experienced operators for reliable communications. Some people also believe that a poorly timed solar minimum in the 1970s was an additional factor that precipitated the decline in HF. Another important factor in the decline of HF was the growth of the Internet. The Internet got people used to very high data rates and more or less instant global connectivity. The Internet was always on, and over time became more or less globally available, particularly in developed countries. The Internet could meet data needs over increasingly larger areas of the world, and where terrestrial Internet wasn't available, satellite was an acceptable substitute. Over time, the decline of interest in and use of HF created a corresponding decrease in funding and mind share, reducing, but not entirely eliminating, interest in HF and the number of trained or experienced HF developers and operators. But with all of their benefits, satellites also suffer from a number of vulnerabilities or weaknesses. A hostile force or bad actor can employ a wide variety of anti-satellite or ASAT technologies designed to temporarily or permanently incapacitate a space vehicle. Ground-based attacks, such as using lasers, are relatively inexpensive and difficult to stop or detect. They can even be used by countries that have no launch capabilities of their own. And for countries with launch capabilities, either ground-based or air-launched weapons can be used to destroy satellites. The United States, the Soviet Union/Russia, and China have all carried out numerous ASAT tests, and many other countries are developing ASAT capabilities. Jamming is another serious vulnerability, in part because satellites are not generally frequency agile and operate at frequencies which are relatively easy to jam. Another threat is solar storms. The same solar flares and coronal mass ejections that cause problems in the ionosphere can and have disrupted satellite communications, and have even been blamed for physical damage to satellites. In addition to these threats to the satellites themselves, it's also important to note that satellites don't always provide truly global coverage. For example, coverage in both polar and oceanic regions has long been a weak spot for many satellites. Not all satellite constellations cover the poles, and those that do, for example Iridium, require a relatively large constellation to do so. Certain terrain or geographical issues can also present a challenge when it comes to satellite coverage. Mountainous regions or areas with significant foliage or canopies, like jungles, can block the direct line of sight needed for most satellite communications. Other limitations include the unwillingness of certain countries to rely even on their own allies' satellites for communications, as well as the very high latency or delay introduced by geosynchronous satellites. But as global connectivity has become more and more mission-critical, there's been an increasing interest in providing a separate technology that can deliver similar global connectivity. Even this connectivity doesn't match the speed and bandwidth provided by satellites. And this is a role that HF is well suited to play. HF provides truly global coverage, including polar regions and regions that are terrain challenged. HF does not require special infrastructure, such as a constellation of satellites. The infrastructure for HF is the ionosphere. This is also one of the reasons why HF is much, much cheaper than satellite, and helps make HF robust against attacks. Solar events may temporarily disrupt HF propagation, but there's no practical way for humans to damage or destroy the ionosphere. And because of the lower frequencies and frequency agility, so to speak, HF communications are much harder to jam compared to satellite. In order to allow HF to meet the minimum requirements for a modern global communications technology, improvement or enhancements over traditional or legacy HF must be implemented. The first of these is improved data performance. Although HF will never match the throughput provided by satellites, a certain minimum data rate is still required for HF to be used in modern applications. Despite the dominance of data, voice or audio are still critical components in a global communication system, and there's substantial room for improvement here compared to legacy HF voice. With regards to propagation, there's little we can do to change the nature of ionospheric or skywave propagation, but we can improve the availability and reliability of this medium by better prediction and measurement, as well as the modern advancements in modulation and error detection and correction. And lastly, we need to improve operation over HF by simplifying the process of selecting a frequency or path and automating the process by which connections are established and maintained or modified. In the remainder of this section of the presentation, we'll discuss some of the different technologies that are used to enable these necessary improvements. Improving availability and operation are closely related, so we'll examine these together. The first and most fundamental question in using HF is which frequency should be used to reach a given station or geographical location. As we saw in the section on HF propagation, this is largely a function of the state of the ionosphere, which in turn is a function of time of day, period in the solar cycle, and any unusual ionospheric conditions. In legacy HF communications, a human operator could usually estimate the maximum usable frequency, antenna type and/or orientation, etc., based solely on their training and experience. In more recent decades, propagation prediction tools such as VOCAP could be used to augment an experienced operator's judgment, or to help less experienced operators determine the best frequency. And if conditions changed, the human operator would recognize this and intervene, usually by changing output power or frequency. But clearly, this approach doesn't scale and is very operator-dependent. The more modern approach, therefore, attempts to handle all of these functions automatically, and this is sometimes referred to as adaptive HF, which is outlined in ITU recommendation F1110-2.1. In adaptive HF, the optimum frequency is selected automatically, the initial communication is established automatically, and the system automatically adapts to changing propagation or congestion/interference when needed. By far the most common way that these principles are implemented is through something called automatic link establishment, or ALE. In ALE, all stations are assigned an address, and that address, or different types of group addresses, is used when calling a station. Stations scan predefined lists of channels or frequencies, and if a station hears itself being called on one of these channels, it then attempts to synchronize with the calling station. The frequencies that are used when trying to call a station are chosen using something called link quality analysis. Stations periodically transmit their address along with a sounding signal. Stations which are currently scanning their list of channels measure the received signal and record this value along with the date, time, and address of the transmitting station. These measurements are used to build up a database that's used when picking a channel for calling a given station. Another useful feature of ALE is the ability to listen to a channel and see if it's already in use, something commonly referred to as occupancy detection, as well as the ability to adapt to changing conditions. First-generation ALE systems date back to the late 1970s and early 1980s, and were all proprietary. In other words, they were not interoperable. By the mid-1980s, the need for interoperability and more advanced features had grown such that a new second generation of ALE was standardized as MIL Standard 188.141a in 1986. This version was interoperable and helped to promote the use of ALE. In fact, ALE became so popular that a third generation was developed and standardized a little over a decade later. Third generation ALE was a substantial step forward in that it supported faster link setup and more reliable setup under noisy conditions, that is, when SNR is low. It supports more efficient allocation of spectrum, allowing more users to share the very limited bandwidth at HF, and it's also more scalable in terms of the number of stations that are supported. Traditionally, bandwidth on HF was allocated as 3 kHz channels. The reason for this particular channel width of 3 kHz is because this bandwidth supports the most common use of HF transmission, namely single sideband voice. In older or legacy HF systems, various types of modems were used to transmit data over voice channels, that is, within the same 3 kHz bandwidth that had been used for voice. There are a very large number of different modulation schemes that have been used to transmit data over HF, and over time many of these have come and gone. In the early days of HF communications, FSK, or frequency shift keying, was the most common modulation scheme, and PSK, or phase shift keying, has also been widely used. There then followed so-called M-ary modes like MFSK, where the number of symbols or states was increased to provide greater throughput. And over the last couple of decades, there's been a steady increase in even higher order modulation schemes, such as variants of QAM, or quadrature amplitude modulation, as well as the use of multi-carrier systems like OFDM, or orthogonal frequency division multiplexing. And even voice has undergone a transformation, with modernized HF systems often sending voice digitally over data channels, which typically provides a much higher quality than traditional analog voice. When it comes to sending digital data, or bits, HF is almost certainly the worst possible transport medium. It's noisy and variable, and fading is common. Often errors come in the form of burst errors, where many bits in a row are errored or corrupted by bursts of noise or sudden fades. In legacy HF, it was not easy to either detect or correct bit errors, and this in turn limited the transmission speeds. Since we have little control over the medium, different methods have been developed to help deal with the issue of bit errors in modern HF data communications. One method of combating burst errors is to use interleaving, to spread out burst errors over a larger number of bits. This greatly improves the efficiency of another technique called forward error correction, or FEC. FEC adds additional bits to the transmitted data, which can then be used to detect and correct single bit errors at the receiver. Because FEC can only help with single bit errors, interleaving is important for avoiding multiple contiguous bit errors. For those cases when errors are uncorrectable, a higher level process called automatic repeat request, or ARC, is used to request retransmission at the packet level. Although they may seem to be somewhat mundane, the introduction of these techniques into HF data communications was critical for the improvement of HF data throughput as well as HF data reliability. Increasing bandwidth is one key to increasing throughput. Some early attempts at improving on the standard 3 kHz wide HF channel involved using additional independent sidebands. Although the use of multiple smaller channels does increase throughput, the use of a single larger channel can provide better performance, and this is the reason for the development of wideband HF. The most important current standard for wideband HF is MIL Standard 188-110D, updated in 2017. It defines contiguous bandwidths of up to 48 kHz in various steps, allowing the waveform to be adapted to the available spectrum. Data rates of up to 240 kilobits per second have been achieved on a 48 kHz channel. Another advantage of this wider waveform is increased robustness in hostile environments. A wider signal is harder to detect because the energy is spread out over a larger bandwidth, and wider signals are also more resistant to jamming attacks. And perhaps most importantly, wideband HF has already been successfully used in numerous military trials. Wideband HF is more than just wider bandwidth. It also includes improvements in modulation types and error reduction methods such as FEC and interleaving. Of particular interest are the modulation types used in wideband HF. In addition to traditional or standard phase shift keying, specially designed QAM or quadrature amplitude modulation variants are also included. These variants have modulation orders up to 256 QAM, with the highest modulation orders enabling higher throughput. Of special interest is the fact that these constellations are circular, as opposed to the more square QAM constellations seen in most other applications. These circular constellations have the advantage of reducing the peak-to-average ratio of the signal, which in turn simplifies both the design and efficiency of radios and amplifiers. The development of fourth generation or wideband ALE is largely being driven by the rollout of wideband HF. Because wideband HF supports different bandwidths, modulation types, error detection and correction schemes, etc., 4G ALE is a critical component in ensuring that stations are able to exchange capabilities, intended traffic types, and negotiate appropriate parameters. Similar to previous versions of ALE, 4G ALE also supports more advanced forms of spectrum sensing for determining the optimal frequency and bandwidth that are needed for a given connection, and it incorporates numerous features for both wideband as well as traditional narrowband HF. So let's summarize the main points with regards to HF communications. As we've seen, satellite largely replaced legacy HF for global communications beginning around the 1970s and continuing to this day. There are many reasons for this, the most important of which is the much higher throughput provided by satellites. Satellite communications, for the most part, are unlike skywave HF in that they're not dependent on variable and somewhat unpredictable propagation. And satellite systems were generally much easier to use than HF, and did not require highly skilled or experienced operators to establish and maintain communications. That said, satellites are much more expensive than HF, are vulnerable to a variety of attacks, and may not provide global coverage in some cases. Due to the mission-critical nature of global data communications, there's a strong need for an alternative or redundant system. Although traditional or legacy HF pose significant challenges in many areas, modernized HF has eliminated, or at least reduced, many of these shortcomings. In particular, recent developments in both wideband HF as well as the newer generations of ALE have increased throughput, reliability, and ease of use, and have helped to bring about a rebirth of HF. This concludes our presentation, The Rebirth of HF. Thanks for watching.